Steel concrete composite structures are becoming increasingly popular in construction industry. When we combine two materials together, steel and concrete, it utilizes the desirable properties of both materials. Steel is equally strong in tension and compression, and concrete is very strong in compression. When we combine two materials, it produces a composite material which is fast, which is efficient, and building services friendly. In this presentation, I'm going to talk about my research when I was a PhD student at University of Leeds, and it was during my first year. There was international conference where I presented this paper. This is about behavior of headed shear stud in composite beams with profile sheetings. What does it mean by composite beam? A composite beam is a beam where we weld shear studs or metal fixings through the sheeting to the beam, and we pour concrete on top of that, and we add mesh reinforcement for shrinkage cracking, and together it forms a composite beam with profile sheeting or metal decking slab. When we have a composite structure, forces between these two elements have to be transferred. Now, how do we transfer these forces? We use shear studs to transfer shear forces between a composite slab and a beam. And normally we use headed round shear studs. And today we will study the behavior of these shear studs within composite beams. This is how my today's presentation is organized: introduction, objectives, FE model and material models, results, and finally conclusions. So let's dive into today's presentation. Headed shear studs are the most common ones that we use to ensure composite action in steel concrete composite beams. Although there are other connectors as well, like channel connectors, like angle connectors, but we use these in bridges. In buildings, most of the time we use headed shear connectors. Both large-scale beam tests and small-scale push tests can be used to study behavior of these shear studs. But generally, push tests are more common to study behavior of studs. A push test is a short replica of a beam test where we have a short beam connected with two small composite slabs. The capacity of shear stud is determined by dividing failure load with number of studs, and in that way it gives us capacity or resistance per stud. The slip between beam and slab is plotted against the load per stud, and usually this is average slip that is happening between a beam and a slab. What are objectives of this study? In this study, numerical investigation is carried out on headed shear studs in composite beams with profile sheeting. A three-dimensional finite element model using abacus was prepared for a push test. The key feature is that both material and geometric nonlinearities were considered in this study. But this was really very initial study of my PhD study, so outcome of research is not as you would expect as the end of my PhD study. And then results obtained from the numerical model are compared with the experimental results. So in simple words, this is a validation study only. In most of numerical studies or finite element studies, you will validate the model first, and then you will carry out a parametric study to add experimental studies. But here I did not carry out parametric study for this paper. This was the experimental study that I modeled using abacus, and it was taken from Lloyds and Wright 1990, and I will put the paper down below in description. You can have a look at that reference. The size of the beam was 178/102 by 19, and only one rib of the push test was modeled. It is a quarter symmetric model. It means that only 1/4 of the test is modeled, but for simplicity only one rib is modeled. Now there are benefits and there are some doubts in this modeling strategy. Ideally, full test should be modeled so that you can see the actual behavior of stud within the profile sheeting slab. But for simplicity, I just modeled one profile sheeting rib. Now what it will not do is that it will not capture certain failures. So here failure is always going to be in concrete. How about if concrete is very strong? In that case, stud should fail, but for that you have to model the entire structure, and I figured out late in my PhD study. At that time I did not know. And also there are certain other assumptions as well which are not as realistic as I would like them to be, but because this was initial study, so any learning or any research is fine. That leads to more refinement of research later when you become expert in the area. The headed studs, they were welded through the sheeting to the beam, and 50 millimeter deep profile sheeting deck was used. Average width of the deck was 150 millimeter and sheeting thickness is really tiny. It's 1.2 millimeter. As I mentioned earlier, only one profile sheeting rib is modeled, and here you can see the finite element model for that profile sheeting rib. Because of the symmetry, only quarter symmetric model is prepared. A combination of wedge and brick elements were used for steel and concrete slab. Profile sheeting, on the other hand, is modeled using shell elements, and 4 noded shell elements are the most common ones, and I used those elements. The wire mesh was modeled as rectangular elements as well. Ideally, wire mesh should be modeled using truss elements, and it should be embedded inside concrete slab, but at that time I didn't know that modeling strategy, so I used the solid element. I converted circular or round area from the wire mesh into a rectangular area, and then I assigned those properties. But this is not a very realistic way to model mesh reinforcement, but now I know. You can see my other presentation by clicking over here, where things are much more improved. Nodes behind the shear stud in the direction of shear loading, they were detached from surrounding concrete nodes. So when you push it, the nodes behind concrete, they will detach, and you will see in failure modes in a minute that how does it behave. This brings me to boundary conditions. So surface 1 was the middle web of the beam. It was not allowed to move in X direction, which was vertical direction, and surface 2, which represents the symmetry boundary condition, it was not allowed to move in Y direction, and surface 3, which represented the support at the end, that was not allowed to move in Z direction. And a uniform load was applied on beam using a Rick's procedure available in Abacus. Now, what is Rick's procedure? This is a procedure where you give some stopping criteria, that if load reaches to a certain point, you should stop, or if deflection reaches to a certain point, you should stop, and it gives increments depending on the convergence of the model. If the model is behaving really properly, converging, then it will increase the increments. If it is not converging, then it will reduce the increments, and everything is automatic, and it's a very good procedure for modeling these kind of composite structures. Rick's method is generally used to predict unstable and non-linear collapse of a structure, so that's the reason I used this method. And it uses the load magnitude as additional unknown and solves simultaneously for loads and displacements. The analysis can be stopped by either specifying a maximum load or maximum displacement at a given degree of freedom. Now, what were the contact interactions? The contact pair algorithm was used to define contact between concrete and profile sheeting, and between steel beam and profile sheeting. Between steel beam and profile sheeting, I assumed the default tangential contact behavior. It was frictionless because there was no friction at all. It wasn't necessary as well, and default normal contact behavior was assumed, which was normally hard pressure contact over closure relationship. And for concrete slab and metal deck, the normal behavior was default hard contact pressure over closure, and tangential behavior used the penalty frictional formulation with a coefficient of friction of 0.45. These are the material properties for stud, profile sheeting, mesh, and steel beam. An elastic plastic model was used for all the steel elements, which means that stress strain behavior, it goes to plastic range and then it is a flat region, which means I will only define modulus of elasticity and I will define the yield stress. The yield stress of shear stud is 470.8. Now you would say that how did you measure this so accurately that you're giving this value in points? I did not measure it. I took the value from the paper and it is given in the paper, and they would have done some tensile coupon testing on the steel elements. And profile sheeting 184 and 308, mesh reinforcement 200 and 460. Yield stress, it's quite high. Normally it's about 350. Steel beam, it was 189, 288. The first value that I mentioned, it is Young's modulus. The second value is yield stress. Concrete material properties here are really very crucial, and the best material that you could use for modeling these kind of structures is concrete damage plasticity. But because at that time I did not know much about concrete damage plasticity and I didn't know how to use it, but later in my other presentations in the playlist you will see that I've used concrete damage plasticity, but here I've used a combination of elastic plastic plus Drucker-Prager model. Now, stress strain behavior of concrete is divided into two parts. One is the elastic part, where you have from 0 to 0.5 FC, where FC is the concrete cylinder strength in abacus, and this part is defined by elastic modulus, and I use this formula 4700 under root FC from American Concrete Institute to define this part. The other portion is from 0.5 FC to FC. For this, the strain is 0.00024 under root FCU. This is from BS 8110, which is a British standard, and that's how I found out strain. And finally, the softening part, where the curves goes down, RFC, where R is 1 for 30 MPa concrete and R is 0.5 for 100 MPa concrete. Now this part is defined by Drucker-Prager yield criteria, where the angle is 20 degree and K parameters is 0.8, and you can find more details in my paper, which I will provide in description down below, or it will be at the end of the slide as well. This is load slip behavior, and you can observe here that the finite element model, it matched really very closely with experiment, and at that time I was really very happy that the job is done. But the job wasn't done actually, because here in most of load slip behaviors you will not see the softening part in the actual paper where experiments were carried out. And I had that fake confidence at that time that yes, this model is correct, but actually there are better ways to model this structure. In this modeling approach, what would happen is that the load is not going to drop. So when the load is not going to drop, the only way to determine failure is to have a look at stresses. So you see at stresses, if the significant chunk of the element, so for example a stud or concrete, if it is failing, if it is reaching a stress, then you say that it has now failed. Now this is a very crude way of determining a failure load. The ideal way is that the modeling should go up and then again it should go down to give exact accurate failure load. And that's what I did later in my PhD study, where I used concrete damage plasticity, where I used full models to model this structure, and which is a better strategy as well. And you can see one paper being presented in the playlist, a deformed shape. Now this was a really very important finding at that time, because everyone else at that time, 2009, everyone else was modeling it as it is attached. So sheeting was assumed to be attached with the concrete, which is not a realistic way, but I assumed a contact pair algorithm between sheeting and concrete, and that resulted in separation of steel deck from concrete, which is a realistic behavior when you use it in a push test as well. And I was very pleased with this result. So the bond between steel deck and concrete, it breaks when you apply more loading. So as a result, the concrete slab will move and ride over headed shear studs. And this is the realistic behavior. That's what happens in experiments. Separation of steel deck from concrete is one of the key findings of this research, at least at that time. This slide shows the stress contours. You will see that how concrete is failing. The stress is not more than, I think, 35 MPa, which was the actual concrete properties of this test. You will see that the concrete behind shear stud, it has cracked. This is a cut view of slab, and here you will see concrete cracking. Now see that concrete behind shear stud is failing. That is indicated by red contour plots, and finally it's failing quite a lot actually. Now this slide shows deformation in sheeting only, where concrete slab is removed, and that kind of deformation is really very similar to what you would see in experimental push test. Stud is moving on one side and there is some kind of buckling happening in sheeting, and finally failure happens in concrete. These are results for all models. So there was a lot of experiments in this study by Lloyds and Wright, and I've modeled all those studies. And here you can see P test means that shear capacity per stud in the test, and you can see PFEA, which means that the results obtained from finite element model. Now results were really very close, with the standard deviation of 0.036 and coefficient of variation of 0.039, which indicates the successful modeling, and I was really very happy at that time. I thought I got my PhD, but later I found out that a lot needs to be done. Now this brings me to conclusions. One of the key conclusions of this research was that the separation between steel deck and concrete was modeled, and that is the realistic behavior of a push test or in steel concrete composite beams with profile sheeting. And also I was able to predict the load per stud accurately as compared to the experimental results, and also that gave me confidence to carry out parametric study by changing the size of the stud, changing the size of the slab, or maybe different profile sheeting and a different mesh size and concrete grade as well. One thing about finite element modeling is that if it is validated really very properly against a set of experiments, not just from one paper but variety of paper with variety of situations, and by changing the mesh sizes, by changing the load patterns, and by capturing all the failure modes, then it can be a very useful tool that can really help support experimental study and in carrying out the theoretical studies as well. You can download a copy of this paper by going to this webpage, tinyurl.com/jq-ACCS2009, or you can use this barcode to scan and go to the website directly. Thanks for watching this presentation today. I hope you enjoyed the presentation a lot. I know that this is really very initial study, but for some people it might benefit them who are starting to model these kind of structures. I will see you in my next presentation. Until then, goodbye. Thanks. And again, if you have any questions, please put them down in comments. I'll be able to respond. What is a push test? A push test is a replica of a beam, and we use push test to determine the shear resistance of shear connectors. What are shear connectors? Shear connectors are metal fixing that we weld at top of the steel beam, and on top of that we pour